Hi everybody, Jonathan here. In this video, I'll be giving you my take on section 4.8, which is all about Newton's method. Newton's method is a great way to find an approximate solution to a root of a function, which is just a fancy way of finding a solution to the function equaling 0. Now, the main idea of Newton's method, imagine you've got the graph of your polynomial, or function, as seen here. And here we've got a root at some value. So the idea is that you find an x value that you think will be close to the root. So the book is calling that x1. And then you can make the tangent line at the point x1 f of x1. Now, if the x1 was reasonably close to the root, you can look at where the tangent line crosses the x-axis, and that'll be closer to the root than the original point. And then you can repeat the process for that new point, and you keep on repeating the process, and if things go well, which they don't always, but if things go well, then you'll get a sequence, x1, x2, x3, where each term gets closer and closer to the root, and you can go as long as you need to in order to get as close to the root as you need to. So the equation of the tangent line at our point x1 f of x1 is y minus f of x1 equals f prime of x1 times x minus x1. So if we want to find the root of the tangent line, where the tangent line crosses, we just set y equal to 0, and then we just have to solve for x. So solving this equation for x, which they're just calling x2 because that's the next point in this process, you wind up with x2 is x1 minus f of x1 over f prime of x1. Again, we're just solving this equation for x2 in this case. And all your subsequent iterations, x3, for example, will be x2 minus f of x2 over f prime of x2, and so on and so on. Xn plus 1 will equal xn minus f of xn over f prime of xn. And as you can see from this picture, the tangent line roots are getting closer and closer to the actual root. So I made a GeoGebra app that will allow us to play around with these ideas and see how it works. So, for example, let's find a root of x squared minus 5. So, of course, this is kind of exciting because the root of x squared minus 5 is also known as the square root of 5. Of course, if you set this equal to 0 and solve for x, x will be the square root of 5. So what Newton's method is really giving us is a way of finding a way to approximate or even calculate things like square roots. So what we have to do is we have to choose our first x value that we think will be close to the root. And you don't even have to be that close in this example. I'm just going to be like, yeah, let's try 5. Now if we make the tangent line at 5, zoom out a little bit, then you can see that the tangent line is crossing. Here it's crossing at the x value 3. And what we can do now is change the xn to be 3, and then we'll get a new tangent line. And the root of our new tangent line will be even closer to the true root. So now we've got a 2.333. So I'm going to change the xn to 2.333, and then we'll get even closer to the root. Now, and this black point here is actually the where the tangent line is being formed, so when that black point gets to be on the x-axis, we'll know we're there. At any rate, now the new x value is 2.2381, so I can try doing that, 2.2381. And now we're really, really, really close. It's not entirely on the x-axis, but it's close enough for government work, as my dad used to say. So we get that the square root of 5 is therefore really close to 2.23607. And just for fun, I will type in the square root of 5, and let's see what the actual value of the square root of 5 is. So it's 2.23607 when you round. So we actually got it completely accurate out to 5 decimal places. So now I've got a new function in here just to show how this works for any function. This new function is x cubed over 10 minus 2x squared plus 7x plus 2. So if we zoom in a little bit, we'll see we have a root and it's pretty close to 0. So we're going to have our first x value be close to 0. And now we'll show the tangent line at that point. And already we are really close to that root. The root of the tangent line is super close, and it's saying there's minus 2.8571. So I'll just type that in, minus 0.28571 for the next value. And now I get minus 0.26544. Again, once this black dot lies on the x-axis, then we'll be there very close. So let me try this next one. So 2.6544. And wow, we're right there. So whatever the root is, now it's saying the next one would be minus 2.26533. So this is an incredibly complicated polynomial. Finding the root exactly is incredibly difficult, but you can use this process to very quickly get an approximation. Now, I mentioned that things can and do go wrong if you don't choose that initial point carefully enough, or perhaps if the function is just really poorly behaved. So in this example, I've let the polynomial be x cubed over 3 minus x squared over 2 minus 5x plus 12. Now, suppose we were super lazy and we just tried to have the initial guess of the root be 0, even though you can tell from the graph the initial guess is minus 4 and change. So now when we look at the tangent line, we're actually being taken further from the root. So the tangent line of our first point at 0 now crosses, I guess, at 2.4, or that's the root of the tangent line. So if I do 2.4 as the next point, now the new tangent line crosses over at 3.456. So 3.45366. And I don't even know what's going to happen now. The new point is now 2.5848. And wow, I mean, these tangent lines are all over the place, but we're not getting anywhere near the root. So 4.23587. Yeah, I mean, that's bouncing around, but the roots of the tangent lines are nowhere near the actual root, which is way over here. So if you choose the initial point too far from the actual root, then this process will never get you close to the actual root. Now, finally, I would just talk about what's the point of Newton's method? For example, if I just have the graph, why can't I just zoom in really close up on the graph and use that to try and estimate the polynomial, or I'm sorry, to estimate the root? And you certainly can do that. So if you only have one function and you only care about one root, then yeah, graphing it is a great way of finding it. However, Newton's method is going to be billions of times faster. So in real life applications where you need to find lots and lots of roots and lots of solutions to equations, graphing is incredibly slow. So the time it takes for the computer to graph it, it could have found many roots using Newton's method. And furthermore, you can also use Newton's method to find cube roots and fifth roots of any number. For example, if you want to find the cube root of 7, that's going to be a root of the function f of x equals x cubed minus 7. And you're wondering, well, why can't I just have my calculator tell you that? Well, how do you think your calculator finds something like the cube root of 7? In many cases, it does algorithms similar to Newton's method. So all this stuff is incredibly useful once you want to get into the land of programming mathematics. All right, that's all for now. See you next time.